welcome everybody. Thank you for joining. 128 and counting. Hi Caesar. We're talking today about design of experiments. So we're looking at sort of improving designs to improve the accuracy of genetic effects. For those that have just joined, questions, please pop in the question section. Any chats, any hellos, any specific things that you're looking to cover, please pop that in the chat. All the recordings will be sent after the webinar, along with the presentations and answers to any questions that are raised during the webinar. I think that covers everything. I will pass you over to Salvador.
Hello, good morning, good afternoon, or good night. So thank you for joining us again. I'm just going to be putting my my slides up. And then we'll be good to go. View, let's put full screen. Full screen, so you can see everything. So today I wanted to talk about slightly different topics. I don't want to show too much of elements related to software, but I'm still going to mention a few software to generate designs. But the main idea is to think about experimental designs and its elements and see how this one, and think how these elements actually can lead us to get some improved designs and in some cases optimized designs. All of these with the aim of generating better designs for field trials. I work in forestry, and most of you work in agriculture or forestry. So this should give you a few ideas of things that you could do or you could not do, and to take into consideration when you design experiments. And I also will give you a few new ideas, hopefully, of slightly extensions to some of the designs and slightly different ways to think about these designs when you're going to be using in your trials. So the first thing is just a little bit to walk you through design of experiments, or DOE. I'll be using the DOE abbreviation. We use them to evaluate and compare different conditions. And in our case, most of these conditions are the genotypes or our treatments. Often we deal with clones and genotypes. Sometimes we deal with specific individuals to estimate breeding values. Other few things we need to consider when we design these experiments is obviously our experimental units, our measurement units. I like to make the distinction between those. Measurement units, sometimes we measure each individual plant, but we have plants grouped in plots. And we obviously want to know performance of the overall plot. We also have to think on the design of experiments about the background noise or random noise, and sometimes a bit less random. Sometimes we have more control of what happens, but often it's something that is always there and is going to affect us. And finally, something we don't really consider too much in our field experiments for genetics, it's the specific hypothesis, but in some cases we do have hypotheses, but obviously we should design our experiment thinking about what are our main hypotheses. The principles of experimental designs that we probably all have already studied are randomization, replication, and blocking. And they are very critical in all these steps, and that's the examples I'm going to be using. In the case of randomization, we always think about assigning the treatments without bias to the different experimental units. And without bias means we don't have any control. Hopefully, it's all done in a random way. We don't put our own perception, our own bias in how we're going to assign or even how we are going to measure those specific treatments. Replication, we refer to having copies of the same treatment so we can have some estimation and separation of the signal from the noise. And in that particular case, we think about having more than one representation of that noise so we can estimate a variance component, which is the MSE, mean square error. And that's very important because all the statistical inference will rely on having a good estimation of that background noise. And then the blocking helped us, again, to kind of control We are lucky to work in a field, so we have the plants in the same spot, and we can use different blocking structures, different types of blocks to define and to kind of separate some of the environmental variation and have a better comparison of the treatments with similar units. That's the whole idea of the blocking. So let me just start with randomization. Randomization is always for us an insurance against anything that we might think it might have a bias. Let me just move this thing out. I don't want it here. So anything that helped me to remove that potential bias that I might have. And so it guards me against some potential improper allocation of the units. And then we know we can do randomizations in different ways with random numbers and so on. The computers help a lot with this. Now, the main idea of this is that we allow the comparisons of the treatments to be unbiased. In that case, it's considering that there's many possible randomizations, and the one that we have is one of all the possible randomizations we could have used. Because we don't have control over it, or we have very limited control over it, about the randomization, then it also allows to say, well, this is one of the outcomes of this specific experiment, and therefore we can trust that it represents a random outcome of that experiment. And again, you have to think about type 1 and type 2 errors and so on that rely on this sort of potential randomization. Now, when we don't have a randomization and things going into like a sequence way, then we always have this very concern of, do we have we control for everything? Have we taken care of all the aspects? And often we haven't. So having randomization also works a little bit like a peace of mind in general. Now, it's a good practice to also keep some sort of randomization of many other aspects, and one of them is also not knowing what the treatments are, but also having like randomization on the way some of the things are being measured or some of the things that are being processed. All of that will protect you for any potential bias that you might generate. And here I just have a very simple example where we have 3 treatments with 3 replicates each of the treatment. If you have a gradient, just having a randomization will allow you to kind of have that little peace of mind of everything being sampling the different levels of the gradient. And this is just one outcome from all the possible outcomes. Now, randomization is good. And then I'm thinking, is there such a thing as too little randomization of my experiments? And the answer is yes. There is sometimes too little randomization. And this is an example where we have 12 treatments. We have 3 replications, and this experiment, this randomization was used on the same 3 sites. So you can see here the treatment 2, T2, T2, and T2 is located all in the same place. And this is not an unusual case that you see where some scientists use exactly the same randomization, sometimes over years, sometimes over sites, because it's just simple, because it's just easier. But there is hidden effects here. For example, if you were going to harvest given from a given corner, all the trials will be harvested at the beginning and the same period. And that might be that the blades are better or are worse, and it's going to create some sort of gradient or bias in this particular case. There might be other things also when they are planted. Even if the specific sites are going to be probably located with different orientations, you might still have things, for example, that treatment 2 and treatment 8 might have a very strong interaction. And because your randomizations are always having treatment 2 and treatment 8 together on this corner, that interaction is always going to be present. So that represents an unnecessary risk. Even though you have randomization, you don't have enough randomization in your case. Now, there is another typical case on which, this is already just the solution to it, just have different randomizations for each of the different sites. And you provide every treatment to be the possibility to be with any other treatment, to be located in different places and so on, and you can balance this in different ways. But again, it's just a little bit of peace of mind. They're saying that if anything happened there, then, or anything potential confounding effects, I don't need to worry about. Now, the other case is there is such a thing as too much randomization. So this is another case where it's very typical where the randomization is done several times. And in this particular example, what I have is I have an experiment. Imagine you have this in a greenhouse where you have two replications of each of the treatments, rep 1 here and rep 1 there. And you did your randomization. So I have my treatment 5 somewhere, treatment 5 here. But then what happens is that every day, you decide to re-randomize or rearrange the units within a rep. So, for example, in this case, if you do this for 7 days, you have treatment 5 here one day, then another day somewhere here, another day somewhere here, and so on, and everything gets re-randomized and rearranged. That sounds like an excellent idea, because now you're allowing, for example, if there is a strong gradient on the left compared to the right, you allow treatment 5, or this specific plan of treatment 5, to be on the left and then to be on the right and on different places. So effectively, what you're doing is you're allowing the residual of that plant to be averaged over 7 days. So you don't get a residual per se at the time of at the end of the experiment. What you get is an average of residuals that happen in a day over 7 days. Now that it's good because that means when I see the plant, I have residuals kind of average out. But what is the problem with this is that my mean square error or my background variability is totally invalidated because it represents the average over 7 days. And if I have, it's going to be much smaller than MSE than what you will have if you wouldn't have randomized. And that means because it's smaller, your p-values are going to be better, your confidence intervals are going to be smaller. So all the statistical inference gets thrown to the trash, particularly in this particular case. However, what you see, the plans or the averages are still unbiased and probably a bit less variable than what you will expect. So it'll give you that sort of feeling of consistency. But this case, it's not appropriate because of a statistical inference and it shouldn't be followed. So what you have is you have your randomization, and once you finish your randomization, you kind of live with that randomization, and that is the one that is going to sample the variability on the site. It's going to sample potential edge effects, biases that you might have, confounding effects, and that's what it is with this experiment, okay? So there is too much randomization, and there might be too little randomization. Now let me continue a little bit more with the randomization, and then I'll answer a few questions. So we say randomization does not guarantee that any individual randomization will be unbiased. So you have to think that when we do the randomization, it is one picture of a way to randomize things. And that picture doesn't mean everything will be unbiased. It means some things are going to be biased, potentially because where they are located. So, but on the long run, with many randomizations, you will get unbiased variance components and variance effects and so on. And that's what we want. But I'm bringing you this example here where I have two treatments. I have A replications of treatment A and A replication of treatment B. I do my randomization, and I was very unlucky to find all the A's on the left and all the B's on the right. And this is not an impossible occurrence. It's 1 in 12,870, as it says there, but it's a very likely occurrence. And that means if you are suspicious of this, and you think, no, I don't like it because maybe I have a gradient from the left to the right, then I tend to say, well, then this design is not for you. This design requires something different for your peace of mind. And the solution for that is some level of control. So in this particular case, you see here that I have subdivided the whole experiment into 8 units, which are blocks of 2 experimental units. In this case, A, B, and A, B, everything randomized across everything. So you can see here A, B, and A, B, and A, B. In some cases, we have B's together and A's together and so on. This is just one outcome of those randomizations. But because we added that restriction, that additional restriction, now I have more peace of mind. And I say, okay, I'm moving to this randomized complete block design, and I'm much happier. Now, do not forget that this design and any design where you add some restrictions you are going to pay the price with some degrees of freedom. So you also have to evaluate the power of your experiment. I think we have one question around, so this is a good time to answer one of those questions. I can't see the questions, but
I think we're okay. I think at the moment, Salvador, it's mainly just people saying hello and
okay.
So
okay, no problem.
seeing.
Good. So I'll continue with one of the most important elements that usually we have, and this is related to confounding. So the definition there says that a confounder is an extraneous variable whose presence affects the variables being studied so that the results do not reflect the actual relationship between variables under study. So the confounding is when we have some unforeseen effect. It could be some gradient. It could be something we do for measurement. It can be something when we take the samples and measure them in the laboratory later. So something that often we don't see, or we see after the fact, we design the experiment, that confuses, and in this case is going to create a bias on our results. So in this particular experiment, what I have is I have three treatments over 5 blocks. And it could be that this could be established in the field, but for example, let's say I establish, because of restrictions on time, on Monday block 1, on Tuesday block 2, on Wednesday block 3, Thursday block 4, and Friday block 5. Now, what is that going to create? It's going to create that maybe the conditions on Monday are different than the conditions on Friday. And this gets the effect of the day starts to get confounded with the effect of block. Something similar might happen, for example, if you harvest from left to right and the blades go bad, or something happens during the day. So you have potentially an element that confounds the actual effect of the block and the effects of the treatments. Now, this is a common thing to happen, and hopefully it doesn't create bias in our results, but it could create some bias in our results. So I'm going to talk another case of confounding. It's a very similar experiment, but in this case, I have individuals tested within the same family. So for example, I have in block 1, I planted individuals from family A, individual 1, individual 2, individual 3, randomized in from family A. But then on the other block, I planted only individuals from family B, and then only individuals from family E and C and so on, if you go to all the blocks. So as you can see here, the block is going to be confounded with the family effect. And this is not an unusual case in some breeding trials, because sometimes you have the plants ready at different times, and they might be ready by size, and the size might be genetically related to the family, or you group them for, let's say, some maturation levels or so on, and then you put them as family. Now, this creates a confounding with the different blocks. Now, I'm just going to do a little bit of math. And so, for example, if the total genetic variance will be the variance of the family plus the variance of the within family. So what do you have here is I'm separating into family and within family. And my total variance is actually the block family. So I have a variance associated with the block, the block of variance of the block, and the genetic variance, which I have split on these two terms. So I have 3 sources of variation plus the error, just to show you a simple case. Now, if I decide to fit my linear model, and then I say I'm going to not consider the block term, so what is happening is that I put the family term on my model. I have a within family term, which could be the individual within family. And then I have the error variance. So the family, I have this star, is actually now confounded with the block variance, if there is a block variance, because they get summed up. So in this particular case, I'm going to inflate the family variance. And that obviously might induce me to have inflated heritabilities and so on. And then if I ignore the family term, and I'm just going to focus on the within family, because of the confounded between block and family, what I'm going to have is I'm going to have an inflated block variance, which is actually going to have some genetic components into it. So that's not going to be ideal in either case. And so you don't want this to happen. So what is the solution of this? The solution for this is just to use proper randomization and ensure that all the families are represented in all the blocks if you can. Otherwise, you have to find ways to devise this. So why do I keep talking about confounding? Because it's very common. And there's ways that you can exploit it. For example, you can, if I have the measurement confounding with the blocks, you can actually confound both of them, because measurement, let's say a measurement in the morning or measuring in the afternoon, and there's difference between those two time points, you can say, well, I'll do it by block, it doesn't matter, and I'll get it confounded, and you know your block variance is going to be inflated, but you don't care to separate it between a measuring variance and a block variance. You can also add a second source of blocking and say, oh, I'm going to measure in the morning only 1/5 or 1/6 of each of the blocks. And in that case, you're making it not orthogonal, but close to another blocking source that goes across all the blocks. And in that case, you can separate the effect of the measurement with the effects of the block. And as I mentioned before, you can also make some proper randomizations to avoid any of these issues. Randomization on the measurements or randomizations on when you set up the trials in the field. So those things are relatively important. Okay, so now why confounding I consider it so important is because when we have unbalance, and we do have unbalance, it creates issues. So not all the genotypes in all the sites, not all the genotypes in all the blocks. And for example, in this case, I have block 1, 2, and 3, and for whatever reason, a deer ate some of the plots or something happened. And you can see here, block 1 is the best block, but you can see here that treatment C is only being tested on block 1. So there is a potential bias on treatment C to look much better because it's on block 1. And on the same reason, B is the only one that will be unbiased on its estimate because it's being represented in all the blocks, but treatment A is also going to be biased because it's missing on the worst treatment. So those conditions are not on our control, but it's important to kind of identify when you have missingness, what could be potentially the effects of that missingness, and it might maybe mean that you need to eliminate one block in your analysis, or you use a different specifically more different tricks, like some more sophisticated analysis to control for this, or you just have to throw away the whole experiment because of this sort of confounding. So it's very important because otherwise it will create issues. So now let me go to back to some of the designs. So I'm going to extend control, and then I like to start obviously with a randomized complete block design where we have 4 blocks. I'm going to call them replicates here because they're full replicates. And I have 12 treatments, and these are just one randomization. And this is, let's imagine this is how they are in the field. So I have my 12 treatments here, and you can see here that it looks okay, but you might have some concerns. For example, treatment 3 is here, treatment 3 is here, treatment 3 is here, and treatment 3 is here. Are always on the left, and you might say, I'm not very happy with that. Then again, using the same analogy with the A's and B's, this design then is not for you because you are afraid of it. You have some concerns. So we can use incomplete block designs, and are really one of my favorite designs. You split the replicate into smaller units that are relatively more homogeneous. You have only a subset of the trials. You need to use a bit more sophisticated software to generate this. So in order to have every pair of treatments around the same number of times, so that's the concurrency, has to be quite good. So you don't want all the pairs of treatments always the same. That helps with the comparison. And also the incomplete block, when you analyze it, will model some of the spatial variability that you might have here in this smaller unit. So it does a little bit of that spatial analysis. So here we can see now treatment 3 is here, is there, in this case it's here, and then it's there. You still have the chance that it might be all on the left, but now will be with different treatments, so it's less likely to be all always together. and the comparison between treatments tends to be better, okay? So, and then we have the row column design, sometimes just called RC. By the way, this lambda here represents the number of times that every pair of treatments occurs together. So in this case, it's not a balancing complete block design. There's the majority of the treatments are ones, pairs of treatments are ones together. There's a few that you will find they're 2 times together. Now, in the row column design, we extend this idea of having the incomplete blocks as columns within a rep, but we also have them as row within a rep. So now we ensure that treatment 1 and 8 occurs around 1 time in the same column and around a little less than 1 time on the same row. So you have 1 and 8 here, you have 1 and 8 here, and then that's pretty much it. It could be a couple of times twice. Again, it's not totally balanced, but this ensures again that they are sharing slightly different things. And as a side effect, everything gets a little bit more shift. So there's less likely that the same treatment will be always on the left or always on the right, because you're looking for more different combinations. Okay, so it provides with a better control. On top of that, it also helps the row column designs to find different neighbors, and that has some implications when you have competition effects. Okay, so how do we write these models here? Well, it's just briefly, I'll have for the randomized complete block design I show you is rep effect, then we have treatment effect. You can have rep fixed or random, usually fixed. It's balanced, so it's not a problem, and orthogonal to treatments. And then you have the treatment effect, which could be fixed or random depending on what you want. For the incomplete block, you just add an extra term, which is the incomplete block nested within rep. Notice that the design I just showed you was a resolvable incomplete block. It was not balanced, but it's resolvable. So all the treatments are contained within a rep. So this term has to be random. It's the one that describes these little things here. And then you have to have a random because it's not orthogonal to everything. So it's an incomplete block. And then you have the row column designs where you have the row nested within rep and the column nested within rep. Again, random effect because there are incomplete blocks really with slightly different names. And in this case, are one perpendicular to the other. So again, there's many software to generate these designs, and they have quite a bit of efficiency. And if you're dealing with even hundreds of treatments, these are very efficient experimental designs, and they allow for some spatial control. Now, I'm going to extend this control of the space into Latinized and non-Latinized design. So let's assume in this case I have my 4 replicates arranged on this way on the field. I have one full replicate here, another one here, another one here, and so on. If you see treatment 4, it's always on the bottom of this experiment. And if there is a gradient here, which is good or bad being on the bottom, that means 4 will have a little bit of a bias. And notice that 6 is always on the left, on the right of this experiment. So if there is a little bit of a trend on this direction, it will tend to be inflated or deflated by a certain amount. So that might mean, again, I'm not totally happy with this randomization. Do I need to generate one more or so on? But then the option is to use these super blocks, which are the Latinized blocks, and I'll show you the example on the next one, where we actually have said we are going to take the first 3 columns and we're going to define on this set of the first 3 columns going across the first 2 reps to define a super block. But notice that this block has 24 units. Therefore, I have 1 copy of each treatment in here. So here's treatment 1. And then I have another copy on this one, and then on this one, and so on. So I have defined these super blocks to be containing all the treatments, and in this case, they're going to be orthogonal to the reps. almost. But actually they are orthogonal to the treatments. And then you have this, same thing goes in this. I have taken these first two rows, and again, it's 24 treatments exactly. So you will find always one copy of 12, one copy of 12, one copy of 12, and one copy of 12. So this is a Latinized experiment, and you can see now 12 is on the top left, 12 is on the bottom left, 12 is on the bottom right, and 12 is on the top right, well, whatever, in all these corners there. So you can see this looks a lot more appealing, and it's the same for every single treatment. I have added an extra restriction, and that also means that my model gets extended from the typical row column design to a Latinized row column design, where I have added this L row and L column to denote this is the L row 1, this L column 1, L column 2. So I have 4 levels for those factors. They can be fixed or random. If you consider them fixed, in this particular case, it's fine because every treatment is contained in each of these units. If it's not the case, then you might have to define it as random. For example, I could have decided to do these L rows to just consider 2 elements. And in this case, the first 2 columns, then the next 2 columns, and the next 2 columns. So I'll have 6 levels of their long columns. And because they don't have 24, then that means I will not have a full set of the treatments, which is okay. But that means that probably needs to be a random effect. Okay. So, but then there is a few more options. So now the question is.
Sorry, Salvador, could I stop for a second? We've got a few questions. Would it be an okay time just to go over a couple?
No problem.
Yeah, so somebody's asking, are you going to be talking about row column designs without replication?
No, I'm not going to talk about those, but the logic is very similar. Those are the non-resolvable row column designs. So, but I'm not going to talk about them. But there are an option. But I do personally prefer. I prefer to use replicated or resolvable row column designs or resolvable incomplete block designs, because in case something happens with one of your reps and you need to eliminate it completely, then it's a little bit easier. Everything is still kind of orthogonal and so on.
So if you have any specific questions, Kola, please do direct them to us. The software that we're going to be showing you later does manage for that type of design, but just not something that we're presenting today. We've got several other questions, Salvador, but I'm just going to pick one. Somebody is asking if you're going to look at going to provide some insights in a more broad sense around the heritability of trials, and how it's affected and how it affects the experimental design.
Yes, I will talk a little bit about some special designs that use the heritability to be designed, to be generated. So that's a little bit after a few slides ahead.
Lovely. Thanks so much. As I say, just to remind everyone, it's unlikely that we're going to be able to get to all of the questions during the presentations. We've got a lot to cover, but anything that's not answered, we will make sure we get back to you after the webinar. So please bear with us. Thank you. So
normally I'd reply to the questions into another document that you can access later too. So, but again, also feel free to send emails around. So there's a lot of aspects, as you can see. So spatial analysis, I always get this question, is like, well, I'm going to do a spatial analysis, so I shouldn't worry too much about the design of the experiment. And the answer is, it is true. On a spatial analysis, if you're going to use it, it will help you for a bad design. But a bad design is always a bad design, and sometimes it's so bad that there's no statistical technique that will help you to recover. On the other hand, a good design, sometimes you can analyze it without a spatial analysis and you get all the benefits from the spatial analysis anyway. So particularly those like row column designs or incomplete blocks that they are somehow taking care of the spatial variability can be as efficient as any spatial design. But in general, spatial analysis help us to improve things, particularly when there's some level of imbalance, improves the breeding value estimation or the total genetic value estimation, normally tends to increase the heritability because we have a better control of what's going on. And the correlation is a nice thing because it borrows information from the neighbor to correct the current observation or all the neighbors. So there's many ways to do that, and I'm not going to explain how it is analyzed. That's for a different talk, but again, it's quite commonly used. So I just wanted to come back for that because we can generate analysis that consider some form of spatial components. The typical analysis, spatial analysis, is based on autoregressive errors. There's other ways, but I'm just going to focus on autoregressive errors with or without nugget. Now, the unreplicated trials or augmented trials are very typical in agriculture, and they do require, often they are recommended to be used with spatial analysis because of this borrowing of information. And I like to think that this goes a little bit with the replication. The replication is still one. That means each genotype is still replicated only once. However, because of the presence of a spatial correlation, we have more than one unit. We have 1.1, 1.2. I like to think about that we have a little bit more than one replication because the error gets improved. But we don't get to a double replication or a triple duplication, and you can assess this with some simulations, and I have done. The other thing that happens with lack of replication, because this is just very poor replication, the replication occurs through the checks. And the checks are really the ones that are estimating the MSE, are the ones that are actually estimating the genetic variance too. So if you're analyzing these sort of trials, the checks are really having the stick on it. So they're really ruling what's happening in there. So everything else needs to be to consider with a little bit of more carefulness. However, these experiments are very good, even with very poor replication, because they allow me to rank the individuals. And normally the way I like to think about this is that when I select the top 20% of the individuals, I'm going to be sure not all of them are the top 20%, but maybe the top 8% from that top 20 is really going to be, so that 20% when I assess them with replication is going to be very high up, probably higher up in many senses. And the same thing, when you look at the bottom from this experiment, in real life with the true values or with replication, they're still going to be very far in the bottom. So your selection of the streams is good, but the selection within those groups is going to change quite a bit because they sample different error variances and so on. So it's a good rule to think that you have a replication that is slightly more than one, but don't think you have a replication that is more than one. Now, these trials are combined with several sites. So then that's where each of the sites represents one replication, almost like one block. In each of those sites, because you're using a spatial analysis, you might have 1.1 times S replication, and that's going to give you more, and in one sense, more degrees of freedom for what you need. And the main advantage is that because you have G by E on each of those sites, which are blocks, when you calculate the MSE across everything, you tend to average out that G by E. And the same thing goes with the genetic effects. They tend to be averaged out. So these designs can be optimized in different ways, and you can rearrange the checks. I'm not going to talk about that, but you can see an arrangement that is a diagonal here of the checks. I'm using a good number of checks. I think it's 5 in this particular example. You have to decide what is the number. So if you want to optimize this, normally you use 10 to 20% of checks, depends on the size of the experiment. And I do recommend that you use several different checks, levels, the high number of levels of checks, because again, those are the main ones that are going to estimate your genetic variance. These can be optimized. One of the things I wanted to mention about the optimization is this is in diagonal, and there is some other approaches where they randomize it within everywhere, and they try to optimize the location. What you really want is you want some genotypes to be equidistant to the number of checks, and that will allow you to have more balance. So this genotype, for example, might be too far away from some checks. Another one here is close to one check and not too far from another. So the precision of the estimation of the error of this one is going to be better than the precision of this. And that's something you want to balance. Again, there's several software to generate these designs. One little word about the unreplicated trials is that when you are using the pedigree, they are no longer unreplicated. They're actually replicated. Why is that? Is because now if let's consider, for example, these two sites and I have treatment 2 and I have another treatment 2 somewhere, each of these represents a family, and you have different individuals from that same family, and those individuals are a single copy. So because we don't replicate, and particularly in forestry where we use one seed represents one of these genotypes. So they're not identical, and that's still fine. And we have used that for generations, really, in an animal breeding model to separate it. So unreplication in this case is not a problem. You can have the replication as a clonals, and that's going to be great. But when you have a pedigree information and you relate everything through some families, you don't have that problem. Now, what is important there is that the families have to be replicated. You cannot have one individual from a given family unless you have a very good pedigree. So in this case, you might want to ensure that every family is represented on every site, or every male or every female is represented on every site. So your analysis, which I'm not going to talk about here, can be done with some way to estimate the genetic correlation, like a core GH or a factor analytic and so on. So it does help you, but it's less of a concern. Okay, so there's no replication, but because of the pedigree, we do have replication, and all these connections really allow me to estimate and separate the effects, the additive effect from the error effect. Okay, so that's a bit of important. Now, can we generate designs that consider both of these spatial variability that I have talked and these genetic relationships? And the answer is yes. We can generate these designs, and there's a few software around to do it, and you can create your own algorithm. So what I'm showing you here is a bit of the extra math, but for a linear model where I have some fixed effects and random effects, the random effect will be a genetic effect to estimate, for which one I might have a genetic relationship G, which could be based on genomics. So when you construct the mixed model equations and try to solve the system, you have this C matrix that gets inverted into this. And actually, this C rise to 2 is the variance-covariance portion of the random effects, which are your genetic effects. So if you take that I call M, parentheses, this omega, which the omega represents for a specific design, I have this matrix of the number of genotypes by the number of genotypes, which represents the variance of those effects. And you can see here, don't need to do all of this, but you can see that this is not a function of Y. So just needs the design matrix, which is my X, your link with the individuals and so on. So everything is relatively straightforward, but you need variance components to be provided. So what you can do is you can play with this matrix, and you want to say, I want to optimize this matrix by testing different designs. And this is how it's done. So you use that matrix for any specific design. You say, I'm going to maximize the A optimality or the D optimality. By the way, the A optimality is what is used for the incomplete block designs and for the row column designs everywhere around. It is the function to say this design is better than other designs. And in this case, is the minimum value of the trace of or the diagonal of that matrix, which is equivalent to the variances. It's taking the average of the variances of that matrix. So you want to minimize the average of the variances, which makes total sense. And the D optimality is trying to minimize the determinant of that matrix, which is the hypersphere or hyperellipsoid of that. It's a different criteria, also widely used, but computationally more intensive. So what I can do is I can generate hundreds of designs, and I can actually evaluate which one gives me the better A optimality value. Or I can start from one design and swap things until I find the better design. I will need to provide an R matrix and a G matrix. Both of these will tell me, I'm going to say I have a spatial correlation of 0.3 for X, 0.4 for Y, and my heritability is 0.6. For example, and on those conditions, you can generate your design. So I'm just going to show you two results, and this is from some work I did with one student a few years ago. but there is software to do. And this is independent. This is with half-sieve individuals and with full-sieve individuals. The number of genotypes, if I recall well, is 30, but it could be much higher. And the heritabilities are 0.1, 0.3, 0.6, and this is increasing the correlation. So let me focus on low heritability. What you can see here is from the original design, if you start optimizing, you can get up to around 10% better design, which is 10% better A optimality. So a reduction of the confidence intervals of around 10% by re-randomizing the design, particularly for cases with high correlation and low heritability and no relationships. As the correlation goes down, then you have less to gain on rearranging the experiment for either heritability you have. And also you see that as you have more genetic relationships on your experiment, more stronger relationship in your experiment, so that means using the pedigree or the genomic relationship matrices, the benefits of re-randomizing the experiment dissipate because you have more information that you can borrow from here and there. So this is quite sweet in the sense that you can actually improve the design if you have some prior information. And again, there's a lot of discussion about if these are good starting values, do they apply for all the traits or not, how long you have to run the algorithms and so on. So I'm not going too much into that detail, but I just want to show you that there is a possibility. There is another possibility too, and this is other types of designs on which you actually, it's an equal replication. So there's nothing that stops me from leaving one individual out and bringing another individual from a different genotype, especially if there's relationships, because I might have some parents super represented and some others less represented. So if you deal with some unequal replication, then you have a similar pattern, really. So benefits that are similar. Interestingly here, when the correlation is very high, there's less to benefit from any condition. So really, you don't gain too much by optimizing your design when you have high correlations, unless your heritability is too low. So this is an interesting, there is software to do that, but it's possible to generate a design that considers both spatial components and genetic relationship and try to achieve some level of optimization that is going to depend on the conditions. Okay, so again, going a little bit back to the replication, it's just jumping back to the topic of replication. We always think about what is a good replication or what it's, I mean, I'm not talking about power, but it's if I have an experiment with 6 treatments and I have 24 plants that I can establish or 24 plots that you can establish. And this comes from a study I did in cocoa. So I have the 6 genotypes, and can I plant these individual 24 plants all together? Well, the answer is yes. And I have been, somebody suggested this to me, and it's actually totally wrong because in this case, I have no replication because each individual is only once in this particular case, even that I have 24 plants within the plot. So this is the 24 is the pseudo replication in this particular case. Now you can expand this to the extreme case, where we have replication and we have each of the individual plants in one rep. So this is one rep of the 6 treatments, another rep of the 6 treatments, and so on. We have individual plants, and we say, well, now I have 24 reps or 24 blocks. This sounds to be a lot better. And yes, it's going to be a lot better, with the caveat that in this case, you have some competition within the same variety, and here you have competition with other varieties, and that might lead to some other issues. So now let me just show you a little bit more of the ANOVA table, how it looks when we change the number of plants we have in a plot. So between having 1 plant and having 24 plants, and what happens with the ANOVA table if I was going to use the treatments and the blocks as fixed effects. So you can see here that when I have 1 plant, I have the maximum number of degrees of freedom, 115, and that is usually what we recommend often in forestry. We call them these single tree plots, and the individuals are individually assessed with as many replicates, in this case 24, as we can. As you put 2 plants together, 3 plants together, 4, 6, so the degrees of freedom of the error diminish. And obviously now when you're with 5 or 15 degrees of freedom on plots of 6 or 12, you end up with very few replication and you have limited power to test your hypothesis of the treatments. And that's obviously going to be a bit of a problem. Your error variance is going to change because you have more plants per plot. And obviously when you have 24, it's no degrees of freedom, so you can't do anything on your analysis. So one thing is which one is the perfect choice of this. And then again, this is to optimize something on your experiment. You need to decide what is how relevant the competition is on your experiment, but also you need to decide if there is more variability within or between the different treatments. And so that's going to affect a little bit how you analyze this and how you decide your experiment. So going a little bit back to competition effects, which are very important, and that's one of the reasons why sometimes we don't like these experiments, because there might be too much competition between the different treatments. But also sometimes that's why we like this, because we are evaluating the genotype as a crop rather than some individual plant, which is more likely how they're going to be planted. And that's an important decision to do. The competition effects is actually something very critical to consider, okay? They tend to reduce the genetic gains when we have them because they induce some bias on the genetic components, okay? But you can actually have several different types of linear models that consider them, and then they can manage them. So I'm not talking about the models, I can refer you to the literature. But in terms of experiment, there is something quite interesting, which is the neighbor balance designs, which actually will allow me to have one individual to have as neighbor every other treatment the same number of times, or ideally the same number of times. It's a little bit of an imbalance in some cases. And obviously when you have more treatments, it's more difficult that every individual is next to every other individual, but that's possible. So I'm going to show you a Latinized row column design. Here we have, this is the same one as before, we have 4 and 18 are ones together. 4 and 18, sorry, this is a bit shift. 4 and 18 are in diagonal to each other. 4 and 18 are again together, and 4 and 18 and again in diagonal here. So this is not considering anything about, besides the Latinization, anything related to that neighbor balance. But you can consider this neighbor balance in this Latinized row column designs. I did this one with SIG design. And what you have here is that you see now 14 and 8 are never together, but they can be one together. But you can look for other pairs of treatments. 1 and 23 is ones, 1 and 23 is not together, 1 is not together, and 23 is there. So you have a little bit more of a balance. In this case, no pair of treatments are neighbor more than once. So that also, again, is talking about this peace of mind on the design of experiments. When you have this sort of experiments, it gives me that extra peace of mind, and I know I'm controlling for some of those competition effects that I might have in between, okay? So a few more things. I don't have many more slides, but I'll show you a little bit of one software, which is the SIG Design version 8.0, which we have at VSNI. And these are a list of some of the software and R libraries that are available to do things. I have been involved in FieldHub, and we work closely with SIG Design here. And there is a few more R libraries that are interesting. I know this one does some spatial and genetic correlations. I haven't explored it much to know what else it does. I know this Optex from SAS is quite popular to do some complex designs. So at least I know it generates these ones. But there are many other ones that do different things. Okay. And before, I'm just going to show you a little bit of SIG Design in a couple of examples that I have, just to show you how it works. I'm going to generate an incomplete block design with 12 treatments. I have blocks of size 4, and then I'm going to generate a Latinized experiment just to show you how these things go. Let me just jump to that.
Thanks, Salvador. I'm just going to let you know that we're on a 5-minute warning.
Yeah, no problem. So I'm going to go directly to the Latinize. So I have these parameters that is 24 treatments, number of rows and numbers of columns is 4 and 6. I'm not going to do it Latinize in this one. So I don't want it Latinize. Back. And I'm just going to generate this. It says 24, sorry. No, I'll just generate it. So it generates first for rows and columns. And then when you see your output, which is here, you can let it run for a little bit more. And this is the concurrency, which is quite nice. It tells me how many times one pair of treatments. So there's 96 pairs of treatments that occur together in the same row 0 times, 60 that occur 2 times. This is more interesting within the same column. There's no pairs of treatments that occur 2 times together. So this is what you want to have as less number as possible. And here is just the design of the experiment. So it's coming to the side. And these are the different reps and so on. Now I can generate this with a Latinize treatment. So I will say Latinize the first 3 columns, Latinize the 2 rows, and then I'm going to specify the layout that is 2 by 2, okay? And once you generate this, you have, notice, by the way, you can also consider some spatial restrictions, which is it considers some spatial correlation, not genetic relationships, but correlations. And then once you generate it, you will see very similar to what I showed you before. There is different concurrency. It's a little bit worse because I have used those Latinized designs. So there is a price to pay, but you can see treatment 10 is here. Then on the top left, and treatment here is on the bottom right, and then treatment here is on the left of this unit, and then treatment 10 is here. So it does create a little bit of a balance. I need to let it rant a little bit more. Okay, so just the last few words. There are many more options and tools for good design of experiments. And there's also still bad designs of experiments. Okay, so I consider using the design of experiment principles to be crucial. Don't forget them. We have a lot of flexibility to do different things on field trials and our breeding trials. We have different stages and so on, but also that flexibility needs to be evaluated carefully because there is some risk on some of the simplified designs we consider. There is no statistical technique that will recover a bad design. A bad design is always going to lag behind. So just make a little bit of an extra effort for a better design, and then you will have to do less statistical work later on, okay? Now, a poor design is a waste of resources. Time, resources, you spend a lot of time trying to recover something, and often there's not much to recover. If you do a good design, it's all quick, and also you have a better security that you will get higher genetic gains quickly and fine, okay? So I'll go to questions, okay? Carrie, can you help me with the questions?
I can, yeah. There's lots of questions and we've only got 2 minutes to spare. There's a few quite specific questions as well, which we will come back to you on. A lot of people are asking about site design and how to access that. We will be sending you links and details for all the software mentioned today. Site design is not a free package. It is a paid-for package, but again, we'll follow up. We'll follow up with details there. Karimo is also asking, GenStat, is GenStat a free package? No, unfortunately not. GenStat's not a free package, but we can send you some details. I'm happy to allow you to trial that if required. As I say, many questions. Some have actually been covered, and some are sort of particularly relevant to the previous parts that we've talked about. So I think perhaps it's best just to leave the questions for now.
Well, I'll answer a couple of things, Carrie. There's one question about 20% of the checks. I think 20% of the checks is when you have very large experiments. When you have a small experiment, this number usually goes to 10%, but some simulation work will help. Another question was, can we estimate G by E when only one replication? The answer is yes, but you don't have a very good estimation, and the G by E is mostly estimated by the checks, not by the rest. Somebody asked, what are the computational methods or models that you recommend to compute variance components or heritability and unreplicated? I mean, linear mixed models, and I use obviously A's REML for all of this, but you can also use some Bayesian approaches. So with that, I answer a few of the things, but I'll come back to answer directly there. So keep an eye on the answers when we release a document. Okay.
I wasn't expecting you to be able to answer those so quickly, but yes, thank you. And thank you everyone for joining us. We will share recordings, we will share details of all the softwares mentioned, and we will also share the presentation. Do feel free to send through more questions to us via email if you think of something after the webinar. Thank you once again for joining us, and thank you, Salvador.
And thank you for being here. Thank you. See you around.